So in the last lecture we did what? We did our lens maker revision. Now we will do combination of thin lenses. So let me write here combination of thin lenses in contact. So you are taking one lens here, another lens you are placing close to this. There is no gap between these two lenses, and they have a common principal axis here. So let's say this is the common principal axis over here. On this principal axis you will place the object. So here our principal axis. Let's place the object, any object, over here, and let's call it as O, and a ray of light is going through this O, and because of that you are getting a final image at I. Now be very careful, this image I is because of both the lenses. This is lens A, this is lens B. Now we know from our previous lectures that this image I was not at this place if there was only lens A. If there was only lens A, then image must be formed somewhere away from the current position. So here it will be I1. I hope this is clear. Now I1 is what? Intermediate image. The image which is supposed to be formed if there was no lens B. So let's say this is your object distance U. This is negative, this will be negative. This is your image distance V, final image distance, and intermediate image distance is V1. We will make use of very important concept here. Let's say the focal length of the first lens is f1 and the focal length of the second lens is f2. So what we can say, for lens A, 1 by V minus 1 by U equals 1 by F. Lens maker's formula. So this will be 1 by F1 and this will be 1 by V1. What is 1 by V1? The image formed by the first lens. This is our equation 1. Now we know that the image formed by the first lens that acts as an object for the second lens. Let me repeat. The image formed by the first lens that acts as an object for the second lens. So for lens B, 1 by V minus, this is what? This is the final image, 1 by V1. Why 1 by V1? Because this is acting as an object for the second lens, equals to 1 by F. This is equation number 2. If I add equation 1 and equation 2, 1 by V1 will cancel in both the cases and you left with 1 by V minus 1 by U. That will be equals to 1 by F1 plus 1 by F2. Now what is 1 by V minus 1 by U? That is your combined focal length 1 by F. That will be equals to the sum of individual focal lengths 1 by F1 and 1 by F2. Now what we have learnt as power. Power is inverse of focal length. So here 1 by F is nothing but P, and the combined power of these two lenses will be the sum of the individual powers of these two lenses. Now if there are n thin lenses, n means any n number of thin lenses, then the combined focal length expression can be written as 1 by F will be equals to 1 by F1 plus 1 by F2 plus ... 1 by F. Similarly, the combined power can be written as P1 plus P2 plus ... Pn. These are the two important expressions while solving the numericals. I hope this is clear. Let's move to our next part, that is prism. So our next topic is prism. Let's draw the diagram for prism. So let me draw a prism over here. Let's say this is my prism. Okay. Let's draw it here. Let's name this prism as A, B, and C. Let's draw an incident ray here. So this will be incident ray here. A ray which is going and hitting the face AB. This is incident ray AB. Okay, incident ray. And let's draw the normal. Normal means perpendicular to the surface. Which surface? AB. So this is perpendicular 90 degree to the AB. Normal. At the point of incidence. This ray will go parallel to the base. And let's draw here our perpendicular here to the surface AC. And this refracted ray, this was a refracted ray. This is coming out on the other face as this. Since it is going from denser to rarer, it will bend away from them. This angle is called as angle of incidence. This angle is called as angle of refraction, R1 and R2. This angle is called as angle of emergence because that ray is emergent ray. So the incident ray is this one. The first ray is incident ray. In the medium, it is a refracted ray. And the ray which is coming out from the other face is emergent ray. So the angle made with the normal is angle of emergence. Now if there was no prism, the ray was supposed to go in this direction. This is what? The path of incident ray when there was no prism. So this ray was supposed to go in along this green direction. This is the future of this incident ray. Similarly, if there was no prism, this emergent ray was supposed to come from this side. Which side? This side. So these two green rays are called as extended incident ray and extended emergent ray. And the angle made by both, we call it as angle of deviation. And that is our delta. What is delta? The angle of deviation. Okay. Now let's take this angle as angle 1 and let's take this angle as angle 2. Let's call it as Q and R. Now we know that angle A plus angle Q and R is equals to 180 degree. Sir, why so? Because AQ and R is a cyclic quadrilateral. The sum of its opposite angles will be 180 degree. Now, if you look at the triangle Q and R, in this triangle Q and R, angle R1 plus angle R2 plus angle Q and R is equals to 180 degree. Now, if I substitute here, the equation 1 and equation 2, if you compare, right hand side both has 180 degree. And Q and R is common. So, what can we say? We can say that angle A must be equal to angle R1 plus R2. Let me repeat. If I compare equation 1 with equation 2, then right hand side both has 180 degree. One factor is Q and R. So, the other factor must be equal. Angle A is equals to angle R1 plus angle R2. This is your equation number 3. Very important. We will make use of it later. Now, if you look at the diagram, angle I, that is equals to angle 1 plus angle R1. This angle is equal to this complete angle, vertically opposite angles. And angle E is equals to angle 2 plus angle R1. Again, vertically opposite angles. I hope this is clear. And delta is the exterior angle, so it will be equal to the sum of interior angles, angle 1 plus angle. Yes, this exterior angle is the sum of angle 1 plus angle 2. Now, How can you find angle 1? From the first equation here, angle 1 will be equals to angle I minus angle R1. And from here, angle 2 is equals to angle E minus angle R2. This is R2. There is a slight mistake. This is R2. Let's substitute this value of angle 1 and angle 2 here. So our del will become equal to angle I minus angle R1 plus angle E minus angle R2. Now this del will be written as angle I plus angle E minus angle R1 plus angle R2. Great. Now if we look at equation 3, R1 plus R2 is nothing but angle A. So we can substitute here del is equals to angle I plus angle E minus angle A. I hope this is clear. This is your del, angle I plus angle E minus angle A. This is equation number 4. Let's move to our minimum deviation condition. Minimum deviation condition. So minimum deviation condition will be, for minimum deviation condition, what are these conditions? Angle I must be equals to angle E. Angle R1 must be equal to angle R2, and that is angle R. Both are equal to any particular angle R. And del we will call it as dm. These three conditions are known as minimum deviation conditions. Let's use these conditions and substitute in equations. So if I substitute this condition in equation 3, from 3, angle A will be equals to angle R plus angle R. So angle A is equals to twice of angle R, and angle R will be equals to angle A by equation number 5. And if I substitute this in our equation 4, so from 4, del will become dm. I and E both are equal, so angle I plus angle I minus angle A. So this I can write it as dm plus angle A is equals to twice of angle I, or we can write it as angle I is equals to dm plus angle A whole divided by. This is our equation number 6. So what is the objective of this whole derivation? The objective of this whole derivation is to figure out refractive index. What's the refractive index? Sin I upon sin I. So let's substitute here I. So I is nothing but dm plus angle A whole divided by 2, and R is nothing but sine angle A by 2. This is called the refractive index of this prism. I hope this is clear. Any doubt? Speak. Then I'll go for the next few derivations of this chapter, the last few derivations. Okay. So what we left with now? We left with our optical instruments. So optical instruments, we have simple microscope, compound microscope and telescope. Telescope doesn't have that much of derivation, but only simple and compound microscope. Most importantly, compound microscope. To understand compound microscope, let me explain you the simple microscope initially. So let's say I am looking at any object. Let's say this is my object, and this object here, this has any height h. So let's say this is the object having height h AB, and this is placed on the ground. So let's say this is the ground. This is the ground, horizontal ground on which it is placed. and I am looking at this object from any point, let's say this one. So let's say this is the point from which I am looking at this object. This is the point. And if I am looking at this object from little far, you will find that, let's say if I am sitting here, then what we will find here is, as you are going away from the object, let's say at this point, at the second location, and this is the first location. So as you are going away from this object, what is happening? Our angle changes. This is our angle theta, and this is our second angle. So here in the second case, the angle is smaller compared to the first case, which means if I go more and more closer to the object, the angle increases. And what angle I am talking about? I am talking about this angle made by the object on the eye. So how do we define this angle made by the object on the eye? We define it as theta naught, and if you remember the approximation for tan theta, it's perpendicular over base. So theta naught is equals to AB upon the horizontal distance BC. AB upon BC. Now, when will you see this object clearly from your eyes? If it is formed at least distance of distinction. So let's say the object height is h, and this BC is least distance of distinct division, which is h by d. This is theta. This is the angle made by the object on the eye without any optical instrument. Now, listen very carefully. This is good enough if you can see it from your eyes. But if the things are very small, then even if you place it at this point, you will not be able to see it clearly. So what you will do? You will place a magnifying glass in front of your eyes to enlarge the image. Now let's focus on how the image is formed from such a magnifying glass. And that is called as, first one as simple microscope. Simple microscope. A simple microscope is a simple lens, a convex lens in front of your eyes. So if I place a simple convex lens in front of my eye, and let's say this is my principal axis, then on this principal axis, let's place any object. Which object? The same object AB. AB is placed here, and I am looking from the right hand side here. Okay. So let's see what kind of image is formed here. So we know any ray which is going, let me draw here ray diagram, any ray, okay. What's the important condition to place? This object must be placed between focus and the pole. Why? Because from 10th standard we have learned that if the object is placed between focus and pole, the image will be enlarged. Virtual and erect and enlarged it will be. So we want enlarged image. So here if I draw a ray which is passing from this object, it will go to the lens and it will pass through the focus here. We know this. Second ray, let's draw it, which is passing through this object and the pole. So let me draw it like this, a little like this, which is passing through the object and the pole. Okay, this ray and this ray, they will meet, and the point at which they meet, that point we will get the image, enlarged image, virtual and erect. This is called our A prime, B prime. Now what is the angle made by this image? That is this. So this is our theta I. What is theta I? Theta I is the angle made by the image. That will be equals to AB upon BP. And even or you can use it as A prime B prime upon B prime P. Same thing. If you take the smaller triangle, it will be AB upon BP. And if you take the bigger triangle, it will be a prime b prime upon b prime p. Okay. So theta I is what? AB upon BP, or you can write it as a prime b prime upon b prime p. Now, what is AB? AB is our, this time in this case, H only. The same H which you are using here. Same object you are looking from the simple microscope, right? But what is BP? Now, BP is not D here. BP is what? Any object distance U. Object distance of this object where you are placing it. Great. So, can we find the magnification? So, let me define the formula for magnification. Magnification basically here is angular magnification and not linear magnification. Linear magnification we know, okay, what it was? It was V by U, correct? Here it is angular magnification. That is angle made by the eye, angle by image on the eye upon angle made by the object on the eye. Now, what's the angle made by the image on the eye? Theta I. What's the angle made by the object? Theta O. That will be equals to, what is theta I? H by U whole divided by H by D. So, this is D by U. This is your magnification. Now, this magnification has two cases. One is, these two cases are, let's take it here. This is very important. If you are given with D and U, you can use directly this formula. But sometimes they give you a special cases. Case 1, minimum magnifying power. Case 1, minimum magnifying power. So, for minimum magnifying power, where should we place our object? Our object, if it is placed at the focus, look at this, if this object is shifted to the left hand side and if you keep it at the focus, what will happen? Sir, if object is placed at the focus, image will be formed at infinity, which means it will not be seen, or it will be very far. So, minimum magnifying power, and in that case, U must be equals to the focus. So, what will be the magnification formula? It will become D by F. That is case 1. We will use it in our next derivation, compound microscope. Second is case 2, and that is your maximum magnifying power. Maximum magnifying power. How do we write maximum magnifying power? Now, maximum magnifying power is power when image is formed at D, least distance of distinction. So, let's use our lens formula, to figure out where will be the object should be placed to get this. So, let's use 1 by V minus 1 by U equals to 1 by U equals to 1 by F. And now, if I place here D minus 1 by D, why minus? Because it is on the left hand side. Minus and minus, that will become plus 1 by U. Why plus? Because object is also on the left hand side, equal to 1 by F. Let's multiply the whole equation with minus D. That will become plus 1. That will become minus D by U, and that will become minus D by F. Let's take that on the left hand side, 1 plus D by F, and on the right hand side it will be plus D by U. So, this D by U is nothing but magnification. So, this implies magnification is 1 plus D by F. This is very, very important outcome. That magnification will be, in case of a simple microscope, 1 plus D by F. What is D? Least distance of distinct vision, and F is the focal length of the lens which we have used. Any doubt, speak up. Okay, let's move to our compound microscope and make use of these things which we have solved here. So let me just minimize it. Okay, and okay, go that side, and let's use the concept of compound microscope. Now, before we go to compound microscope, the question is, sir, why do we need a compound microscope? We need a compound microscope because of this limitation which you can see here. 1 plus d by f. If your focal length will keep on decreasing, your magnification will keep on increasing because it's inversely proportional, you can say. But if focal length will keep on increasing, the overall value will be decreasing. But we need a large magnification so that we can magnify small things also, smallest as possible. But this f being very small has a limitations. You can't go beyond a particular value of focal length, very small value of focal length. So what you do, now you combine two lenses. And these two lenses are combined in such a way that this is smaller one and this one is bigger. And they have a common principal axis as usual. So let me write here compound microscope and put a line here so that you don't get confused. So this is compound microscope. Two lenses. We place the object close to the first lens, hence it is called as objective. We place our eye close to the second lens, hence it is called as eyepiece. And if you place any object here, where we are placing now this time? Are we placing it between focus and the pole? No. For the objective, we will not place it between focus and pole. Why? So that the image will be formed on the right hand side of the lens, and that image we want. So let's say the image is formed here on the right hand side, and this is the ray here which is passing through this, and they are meeting. This is the location where we are getting our image formed by the objective. Let's call it as A prime, and this is our AB. Let's call this as focus FO, and here it will be obviously FO. Now be very careful here. The image formed by the first lens, that acts as an object for the second lens. Let me repeat. The image formed by the first lens, that acts as an object for the second lens. And this image is always formed between the pole and the focal point, focus of the eyepiece. Why? So that we can get an image, enlarged image in front of the lens, somewhat like this diagram. I hope this is clear. So let's move and draw it. So first of all, I am drawing here our ray which is passing here through the pole. Let's say this is the ray which is passing through the pole, and then we have our second ray which is passing parallel, and we have another ray which is meeting here, and this is converging here and going like this. So this point we will get our enlarged image here, and this enlarged image is A double prime. Okay, so 2 times magnified, better than the previous case. Okay. Let's write now magnification. What's a magnification? Sir, magnification is, you said, angle made by the image on the eye upon angle made by the object on the eye. Now theta naught is fixed, theta O is fixed, h by d. What is theta I? That we have to find. So what is theta I in this case? Theta I is angle made by the image on the eye. So we can say it is A prime B prime upon A prime P. And theta naught is already our h by d, we already did that. Where we did this h by d? At the beginning. Here it is. Theta naught is fixed. H by d always, without any length system. So we can scroll down and we can substitute. Okay, so let me scroll up only and we can substitute on the right hand side. So here the magnification will become a prime b prime upon h into d upon a prime p. Let's call this a prime p as, what is a prime p? Object distance. For whom? The eyepiece. Let's call it as UE. So this will imply M is equals to, what is a prime b prime? A prime b prime is h prime for the objective upon h into d by UE. And what is h prime upon h? V naught upon U. Linear magnification of the objective into d by UE. That's our magnification. Standard general form of magnification. What are the two cases here? The two cases will be minimum and maximum. So in case of minimum, d by UE will become d by FE. So our magnification will become V naught by U naught, d by FE. From where we got this? Here it is, minimum magnifying power. And maximum magnifying power will be M, which is equals to V naught by U naught. And d by FE will become 1 plus d by FE. From where we got this? From our simple. I hope this is clear. Any doubts, speak up.